Hi, my name's Kris Foster. I work in product management for GraalVM at Oracle Labs, and I'm going to be doing a session today on GraalVM Native Image for containerized applications. Hope you enjoy the content. So what is GraalVM? GraalVM is a Java runtime. We currently support JDK 11 and JDK 17, and the runtime comes with a new JIT compiler that can make your applications run faster and more efficiently. It's available in two flavors: Enterprise, which is the paid for version that has full support and some performance improvements. And we have the community version, which is open source and free to use. It has two unique features over other JVMs. The first of these is a tool we call Native Image. This tool has the ability to take your application and generate a native executable from it. So if you're running on Linux and you have your application, it will generate a single Linux native executable file that has no dependency on the JVM. It's great for containerization, and more on the benefits in a second. The other feature is that we support multiple languages. So you can run JavaScript. We have a Node.js runtime as well. You can run Python, Ruby, WebAssembly, and many more languages on top of the GraalVM platform. But why should you care? If you're using a Java runtime to run your application in kind of a traditional sense, you run your jars on the Java runtime, then switching to GraalVM Enterprise Edition may give you more performance or better performance. So I would urge you to download it, try it out, and run some benchmarks to see how you get on. We're not going to look at that aspect today. We're going to focus on Native Image. And if you recall, Native Image is the technology that lets us take an application and generate a single executable file, native executable file from it. So what are the benefits of that? The first of these is that we have no dependency on the JVM. So if we containerize our application, there's no JVM in there, which means our container is smaller. But that also means that there's less of an attack surface because we need fewer things in the container. And we will see how we can strip things out of the container today to get a smaller and smaller container as we progress. The other benefit, or one of the other benefits, of native executables generated by Native Image is that they start really fast. So we'll look at that again today and see how the start times can go down to tens of milliseconds or hundreds of milliseconds. It's also resource efficient. It uses less memory. So if you're deploying to the cloud, that's going to be of interest. But the best way to explain this is to do it. So without any further ado, let's take a look at how we containerize our Java applications. So we're going to look at how you can containerize a Java application. But first, we need a Java application. So I've written a Spring Boot microservice. It has a single endpoint, and that endpoint generates nonsense verse in the style of Lewis Carroll's Jabberwocky. So as a quick aside, we're going to use a Markov chain. I'm using a library, the Rita library, to do all of the heavy lifting. And a Markov chain is just a kind of a probabilistic model. It helps us model some text. And once we've got that model, we can use that model to generate text that looks like our original text. So we'll wrap that up in a service and expose that as an endpoint, and we'll be able to call that and see that we get this nonsense text return, and then we'll look at how we containerize it. So let's go over to our shell. As I said, it's a Spring Boot application. So if we take a look at our source code, okay, just a basic Spring Boot application. We have one endpoint defined with a request mapping /Jibber there. And all that endpoint does is call this utility class Jabberwocky that I have defined up here. And it calls its generate method. And this method just returns these nonsense strings, which we return to the user. So if we have a look at our utility class, doesn't really do a great deal. It uses this library that I talked about, the Rita library, to create this Markov chain. We've got some text here, which is the text of the Jabberwocky poem. And when the class is created, when the application starts up, it loads that text into the model and uses that, makes that model available for later generating output text. That all sounds a bit abstract. So maybe the best thing to do would be to actually have a look at it in action. I'm using Maven to build my application. I've already got a jar file that's built. So if I just run my jar file, so it's an executable jar file. Excuse my typing. And I'm going to run it in the background so I get my prompt back, my shell back. So the application started, took a little over 1.5 seconds. So now I can call my endpoint. It's running on local host. On port 8080. So let's call it and see what we get back. Great. So we got some nonsense first there. Beware the jub bird. And if I call it again, I'm hoping that I'll get completely different text. 'Twas brillig and the shun. So there we go. That's our basic application. Let's bring it to the foreground, kill it off. And next we want to look at how we can containerize that. So that's our Java app. I've got a basic Docker file here. Take a look inside. Nothing very complicated. It has a base image that wraps up OpenJDK. We're going to use that, and into that we're going to pass our jar file, and we copy that jar file in, and we just call Java as the entry point and pass the jar file to it. So I have a script that builds this into an image. I've already built the image in terms of just keeping this short. I could start the image by hand, but it's more convenient to use Docker Compose, as I will be building a number of these images as the talk progresses. So let's start up my container with Docker Compose. Let's kick it off. We can see, there we go, JDK is started. That's the name I've given to my container. I've also started a couple of other containers up that are going to be useful in looking at the memory usage of the containers that I start. So it'd be good to know things like the size of the container, the startup time, and how the application behaves under stress. Well, I've written some shell scripts that query Docker and get the image size. So from this, we can see the image size. It's about 600 meg. And all this is doing is grabbing the output from Docker inspect and converting it into a pretty little bar chart there. We also can see the size of the jar file that was built, and that's 21 meg. So in the JDK container, we've obviously got the JVM, the Linux distribution, so obviously it's quite big. We can shrink that, and we'll look at how we can do that later on, but right now that's going to be our baseline. So we've got the size of our containers. We could also look at the startup times. Well, 1.8 seconds, about what we expected. And we can also stress test our applications. Again, I've got a script that does this. This calls through to an application underneath called Hey that allows us to run a number of concurrent connections that hit our endpoint over a period of time. So this is going to run for 15 seconds and display some latency figures and also the throughput. So it's returned, and we can see that 95% of our requests returned within 5 milliseconds, which is pretty good. We had a throughput on average of just over 1,000 requests per second. If I run that again, I expect that the latency will improve because the JVM is warming up, it's profiling the code and doing JIT compilation. So we might expect to see some improvements in performance. And yeah, lo and behold, we do. You know, the throughput goes up, the number of requests per second, and also the latency improves. Okay, so there we have our baselines. I'm going to stop my containers, and we're going to look at how we can build a native image next and how we can containerize that native image. So let's move on to building a native executable and containerizing our applications. Okay, so back to the shell. I built my application in a Git repo, and I've used different branches to represent the different stages of the process. So I'm going to check out the next branch. Okay, cool. And this branch contains everything relating to our first native image. So as I'm using Maven to build my application, it'd be nice if Maven could also build my native image. When you install GraalVM, it installs the native image tool, which allows you to build native images from the command line. But we also have the native build tools project in Oracle Labs that provides Maven plugins and Gradle plugins that do this work for you. So we'll have a look in my Maven file, and I'm going to search for my profile that I've added. So I've added a profile to my POM file that allows me to build a native image. So when I call Maven package -p native, it will call this profile. And this profile makes use of the native Maven plugin that knows how to build GraalVM native executables using native image. It's very simple to use. You can specify the name of the output file. In my case, I've called it Jibber. And you can also pass parameters through to the native image build process. So we're going to use Maven to build it. I've already built a native executable from my application, and that's in my target folder. So let's have a look at this. So there it is. I can run it and put it into the background. So it started really quickly in 37 milliseconds. And I can hit the endpoint of my application and I get nonsense text. So the application, my native executable version built with native image of the application works as expected. So let me bring that to the foreground and kill it. And it is just a binary executable. If we were to run LDD on the file, we can see that it's just a Linux executable, and these are the shared object libraries that it's linked into. And we can even do something like this, where we look at the object file for the executable. And we can look inside it. So lots and lots of machine code there, or assembly instructions. Okay, so that's my native executable running, but I want to containerize it. And I do that through a Docker file. So this is my Docker file. It's based on Oracle Linux, a slim version of Oracle Linux. All it really does is takes the executable file, bakes it into the image, and then makes that the entry point for the image. So when I have a script that builds calls Maven to build the native executable and then builds the Docker image from it, but very straightforward. We don't need to run that now. Again, as I'm using Docker Compose, I've updated my Docker Compose file to now start this container as well. So when I do Docker Compose up, it's going to start my JDK version of my application in a container and also my native image version. So we can use those scripts that we were looking at earlier to query our two containers now. So now we can see we've got the jar size there, which is 21 meg. We've got the size of the native executable, 82 meg. So it's quite a bit larger than the jar file. And we've also got the size of the native image container. Again, this is pulling in this information from Docker Inspect. So our Docker container with our native image in is about 200 meg, and our JVM container is about 600 meg. So it's a lot smaller. We can also do the same as we did earlier to look at the startup times. It's not really a shock, but the native image starts very, very fast compared to the JVM. And we can stress test our application as well. Remember, this is using that Hey tool to query the applications. Now I've got two instances of the Hey tool running at the same time. One talking to the JVM container, one talking to the native image container. And we're going to pull the latency and the requests per second out from those. And we get our results back. So the native image container is significantly, 3 milliseconds slower for its 95 percentile latency. So 95% of requests to the native image container come back in 8 milliseconds. For the JVM, that's 5 milliseconds. And the throughput for the JVM is higher than for the native image. And you'll notice that when I run my stress test again, as expected, the JVM improved its performance. The number of requests per second got higher and the latency decreased. But the native image didn't really change because it's statically compiled. It's not doing any profiling. The application doesn't change. But we can still get good performance with it. But can we improve the performance of our native image? So I'll stop my containers. And I guess the answer to that is obviously yes. So we were interested in whether we could improve the performance. Well, yes, we can. And so if I check out my next branch, in this branch, we're going to look at one of the other GCs, garbage collectors, that are available with native image. So I've added a new profile, and this time when I build my native executable, I'm going to enable G1 GC. So there's my original profile, and here's my new profile. And this is what I'm going to be using to build my next iteration of the native image. And this is very similar. We've changed the name. So it's now Jibber-G1. That's the name of the executable that's produced. And we've also enabled the G1 garbage collector for the native image, the native executable that's built. So I use the same Docker file to build the application. I have a different script this time that calls Maven with the new profile, the one that builds the native executable with G1 enabled. G1 is only available on Linux and for Enterprise Edition GraalVM. It's just worth noting that. I've already built the Docker container and I've updated my Docker Compose setup so that it will start this new version of the container as well. So let's start up my containers. Okay, so we can see we've got the original native image base, we've got the JDK, and now we've got NIG1, which is the native image with G1 enabled. So if we run our scripts again, which have now been updated to query all of the containers that we have, we can see that the native executable got larger when we enabled G1. So it weighs in at 112 meg. And consequently, the container we used got a little bit larger as well. That's now at 228 meg in size. What about the startup times? Okay, not much of a difference. I mean, that could be due to noise, that slight difference. But the startup time for our G1 container is about the same as it was for our base native image. And whilst I'm talking, I'll stress test the application as well. So this is going to run for 15 seconds and it's going to hit all three containers and process the statistical information that it gets back and display it as a nice bar chart. Should be done in a second. Okay, so that's our first pass. We could see that the G1, the native image with G1 enabled, now does significantly better in terms of latency. And it also does significantly better in terms of throughput. So if we run that again, for this particular scenario, remember obviously your mileage will vary, depends on what workload you have, which particular GC is the best choice for it. But in this particular scenario, turning on G1 for our native image produced really good results, really good improvements. So we can see that it still seems to be doing better than the JDK, even after the JDK is warmed up. So I'm going to stop my containers. I'm going to stop my containers and we're going to look at how we can improve that even further. So when we added G1, our native executable got a bit larger and so did our container. It'd be nice if we could shrink the container again. And we can do that by perhaps packaging our native executable in a Distroless container. These are containers with almost everything stripped out of them, apart from glibc and a few other things such as certificates and some base files needed. We can do this in native image if we produce what's called a statically linked executable. We're not going to produce a fully statically linked executable. We're going to produce a partially statically linked executable. So we're going to statically link in all of the system libraries required for the executable to run, apart from glibc. And when I say they're statically linked, that means they're going to become part of the application that we bundle up. So I've got that in my next branch of my Git repository. So let's have a look at that. I'm not going to run the stress test, etc. We're just going to have a quick look at how you would do this. So if we look in my POM file, I've added another profile that explains how to do this. So I've added a profile called Distroless. And this, again, is just configured to build the native image in a particular way. And you can see that I've still got G1 GC enabled. But I've also enabled another flag for the native image build. This is static executable with dynamic libc. So everything's going to be statically linked into the executable apart from glibc, which will be dynamically loaded. Okay, again, I've built this into a Docker file. I've built a Docker image out of this using a Docker file. We're going to have a quick look at my Docker file. And the base of this is the Distroless image, which is only about 20 meg in size. And what we do is we copy our native executable into the Distroless container, and that becomes our new image. Again, I've updated my Docker Compose script so that now when I do Docker Compose up, I'm starting all of the other containers I was, but I'm also starting my Distroless container. And if we take a look at the size of our containers, we can see that our Distroless container is now really small. That's only 138 meg. So it's getting towards the size of our native executable. So our container got larger when we enabled G1, but by switching to something like Distroless, we can shrink our container again. So let me stop my containers. And next, we're going to have a look at how we can improve the performance even further. Okay, we want to see how we can improve the performance. And with Enterprise Native Image, we have a feature called Profile Guided Optimizations, or PGO, that allow you to gather profiling information from your native executable and use that in the next iteration of building the native executable. So let's take a look at that. It's a two-step process. First thing I need to do is move to the next branch of my repo. Okay, we've done that. It's a two-step process, like I said. The first step is you instrument your native executable so that it can gather and capture this profiling information. You save that profiling information, and then when the next step is that you use that profiling information to build an optimized binary. We're not going to do that now, but I can show you how I do that in my POM file. It's very straightforward. If I load my POM file and search for PGO, so I have a profile here called PGO-inst. This is for instrumenting the binary. And the important thing here is just this flag that we pass into the native image build, --PGO-instrument. That tells the native image build tool to build an instrumented binary, one that gathers profiling information, and when it dies, saves it to the file system. The next step, I have another profile for that in my POM file, and this profile is called PGO, is to use that profiling information when we're doing the build to generate an optimized binary. And that's done using this flag, --PGO. And we can pass to that flag the location of our profile. And I'm using the default profile here. You can change the name and location of where the profile gets saved. But when I run my application, it's just going to save it in the current directory, a file called default.iprof that contains all of that profiling information. Okay, let's start up all my containers. I've updated my Docker Compose setup, so now that it starts my optimized native executable in a container that I've already built. And just for comparison's sake, I've also built a JLink container. So this is a minimal JRE with our application in it. Okay, so let's start off by looking at the sizes of our containers. Interestingly, our native image, our native executable container with the optimizations. This is the NI PGO container, weighs in at about 119 meg, so it's really small. The size of the container has gone down since has gone down compared to the size for just native image in G1, and that's packaged in a Distroless container. So very small container size. Our JLink container has shrunk a lot. That's down to 225 meg. So that's gone a long way down from our original JDK container, but still much larger than our native image with Distroless container. Let's look at the startup times. I don't expect there'll be any surprises here. The optimized binary starts in about the same time as the other native images, and our JLink container starts in roughly the same time as our Java process. That's kind of what we would expect. And then if we stress test our application, so this is running the stress testing against all of the containers at the same time, we should be able to see whether our optimizations have, like the optimization information we captured has improved the performance at all of the native image. And so our final row here, NI-PGO, that container, well, we've got the same latency, but if we look at the throughput, the requests per second, we can see that the number of requests per second has increased. So that must be because the spread of the latencies has gone down. So we're able to get more requests through with lower latency. So that means more requests per second. Okay, so the performance has improved by using our optimization step. I've got one more thing to show you that we haven't been looking at so far, and that is the memory consumption. So this script just generates a URL to Prometheus, and I'm using Prometheus to display the memory consumption of the various containers in a single graph. The green line here is the memory consumption for our base native image container. That's weighing in slightly over 20 meg. So that's the resident set size. So that's pretty good. Our Java container, the resident set size that's being used for the Java process in that container is slightly over 140 meg. And our optimized native image, which is using the G1 garbage collector, is weighing in at around almost 70 meg, I think. So our optimized one and our G1 weigh in around 70 meg. So that's a classic trade-off where we've swapped some performance. We've got better performance, but at the expense of more memory consumption, but still massively reduced memory consumption. So this has been a bit of a whirlwind tour. We started out with a Java application and seeing how we containerize it. Then we've looked at using native image to generate native executables, and we've containerized those. And then we've gone through the process of squishing the containers by using Distroless, so we can make our containers smaller with the static linking. And we've also looked at how you can use different GCs in native image, the native executables generated by native image. So we have Epsilon, Serial, G1. The one you use depends on your workload, but we've got performance improvements for our work case using G1. We've also seen profile guided optimizations, and this is a way to optimize your native executables even further. And it's worth mentioning that, GraalVM Native Image is supported by Spring Native, Micronaut, Helidon, and Quarkus. So all of these frameworks can target native executables produced by Native Image. They provide tooling and support for use with Native Image. And last thing to say is that this is just one example, but I hope it gives you a taste of the performance improvements that you can get in terms of memory consumption and startup time and container size by looking at native image executables. So thanks for your time today. I hope this has been interesting and has got you thinking about using native image in your containers.